The stars above hold secrets only ancient hands once decoded. Carl Sagan once said, "We are a way for the cosmos to know itself," and that journey began with astonishing tools now vanished from history. This is the story of 25 lost astronomical artifacts that changed the course of stargazing forever. By the end, you will understand how these forgotten instruments, from a 2,000-year-old Greek computer to Chinese oracle bones, each triggered a revolution in our cosmic perspective. How could a device built before the Common Era predict planetary movements with stunning accuracy? And why were star maps so vital they were woven into knotted cords? What forgotten masterpiece of human curiosity calls out to you from the silent depths of time? Spongy stone and shattered wood lay strewn across the seafloor near the island of Antikythera. In the year 1900, sponge divers exploring a Roman shipwreck brought up a lump of corroded bronze, its true nature hidden beneath centuries of marine growth. It seemed like just another piece of junk from the ancient world until decades later, someone noticed a carefully cut gear wheel embedded within the rock. This was the Antikythera mechanism, and its discovery shattered our understanding of ancient technology. Built around the 2nd century before the Common Era, this hand-powered device was an analog computer of breathtaking complexity. Historian Derek J. DeSolla Price dedicated his career to unraveling its secrets, revealing an intricate clockwork of at least 30 interlocking bronze gears housed in a wooden case. By turning a hand crank, an ancient user could advance the mechanism and see the predicted positions of the sun, the moon, and even known planets moving across the sky on a dial. It could forecast lunar and solar eclipses, and some researchers believe it even tracked the cycle of the ancient Olympic Games. The most astonishing part was its use of a differential gear, a complex assembly that allows two rotation speeds to be combined into one. This precise technology would not reappear in the historical record until the sophisticated mechanical clocks of 18th century Europe, over 1,600 years later. Think about that for a moment. A device built before the birth of Christ could simulate the irregular dance of the moon, a calculation so complex it requires a level of astronomical understanding we never attributed to the ancient Greeks. How did such a sophisticated object come to be on a sinking Roman cargo ship? Was it a one-of-a-kind masterpiece from a brilliant workshop in Rhodes, or were there others like it, now lost to time? The mechanism's very existence suggests a Hellenistic world buzzing with mechanical innovation, a golden age of gearwork and cosmic curiosity. Its loss for nearly 2 millennia represents a profound delay in our celestial journey. Imagine if this knowledge had been preserved, if the path of mechanical computation had continued unbroken. Our entire relationship with the cosmos might have accelerated. This first artifact stands as a ghost from a future that never was, a silent witness to the fragile nature of human discovery. That lost language of the stars, a grammar of constellations meticulously recorded on papyrus scrolls, was the life's work of Hipparchus of Nicaea. While the Antikythera mechanism calculated celestial motions, Hipparchus sought to create a permanent, precise record of the sky itself. In the 2nd century before the Common Era, this brilliant astronomer produced star maps of such stunning accuracy that they became the bedrock of Western astronomy for centuries. His catalogue, a detailed inventory of the heavens, plotted the positions and brightness of over 850 stars. He did not just list them, he gave them coordinates, creating a spatial map of the cosmos long before the invention of the telescope. This foundational work was so comprehensive that it heavily influenced the later, more famous star catalogue compiled by Ptolemy in the Almagest. but the original maps by Hipparchus, his own hand-drawn charts, vanished from history. Many scholars point to the catastrophic fire that consumed the great library of Alexandria as the most likely tomb for this irreplaceable treasure, a single disaster erasing a lifetime of observational genius. To measure the stars, Hipparchus relied on sophisticated instruments like the dioptra, a precise sighting tool that allowed him to measure the angles between celestial bodies with remarkable accuracy. It was through this painstaking work that he made his greatest discovery, the precession of the equinoxes. He noticed that the positions of the stars were slowly shifting over time, a gradual wobble in Earth's axis that completes one full cycle every 26,000 years. This was a revolutionary concept, proving that the cosmos was not perfectly fixed and eternal as once believed. Astronomer Owen Gingerich has emphasized how this single insight fundamentally changed positional astronomy. The methods Hipparchus pioneered, his systematic approach to mapping, would echo through the ages, eventually guiding the hands of Renaissance astronomers as they looked up with new wonder. The reasons for the loss of his original maps are a haunting mystery, lost perhaps to the relentless fires of war, the slow decay of papyrus, or simply the chaos of a changing world. Only fragments of his work survive, quoted and referenced by later writers, giving us mere glimpses of his brilliance. Modern scientists have attempted to reconstruct his star maps using these historical fragments, and the results are awe-inspiring. The positions he recorded over 2,000 years ago align with remarkable precision to what our computers calculate today. It makes you wonder, how much further and faster would our understanding of the universe have progressed if those original, detailed charts had survived intact? Every discovery in astronomy stands on the shoulders of giants, and the lost maps of Hipparchus represent a foundational pillar we can only partially see. This legacy of fragile knowledge leads us from the systematic Greek skies to an ancient Chinese artifact where science and celestial myth were inextricably woven together. While Hipparchus was mapping the fixed stars, a brilliant mind in the Han Dynasty court was building a machine to capture the very motion of the heavens. Heng, a poet, artist, and master engineer, looked at the cosmos and saw not just points of light but a great turning engine. His answer was the Armillary sphere, a breathtaking assembly of interlocking bronze rings that modeled the celestial sphere itself. Each polished ring represented a fundamental circle in the sky, the celestial equator, the path of the ecliptic, and others, all arranged with astonishing precision. By sighting along these rings, astronomers could track the complex paths of planets against the backdrop of stars with a new level of accuracy, refining calendars and predicting eclipses with a power that was both scientific and deeply spiritual. The sinologist Joseph Needham's research highlights a truly revolutionary feature. Some of Zhang Heng's largest spheres were driven by water power. Imagine a constant, flowing energy source turning these intricate models, an automated celestial engine that could run day and night, simulating the cosmos without human effort. This was not just a tool for observation, it was one of the earliest examples of a mechanical planetarium, a working model of the universe for both study and wonder. The cultural weight of these devices was immense. In ancient China, astronomy was the emperor's science, a direct link between the harmony of the heavens and his mandate to rule. Predicting an eclipse correctly was not just a scientific triumph, it was a political necessity, a demonstration of the emperor's connection to the cosmic order. Historical records describe these magnificent bronze spheres being used in court ceremonies, where their silent, graceful turning was a potent symbol of imperial power and celestial favor. Yet, despite their sophistication, the original spheres created by Zhang Heng and his successors were lost. They vanished in the fires of rebellion and the chaotic collapses of dynasties, their metal likely melted down for coins or weapons. What knowledge was locked within those precise bronze circles that we have had to painfully rediscover centuries later? If the designs for these water-driven armillary spheres had traveled west along the Silk Road, how might they have transformed European astronomy? Their disappearance created a chasm in our shared scientific history, a forgotten thread of innovation that reminds us how much of our past is built on fragments. This spirit of building machines to measure the sky, however, would find a new and desperate expression in the observatories of medieval Europe. A navigator in the 9th century, crossing the vast emptiness of the desert or the open sea, held the cosmos in the palm of his hand. That cosmos was etched in polished brass, a complex web of pointers and scales known as the Astrolabe. In the Islamic Golden Age, this was the ultimate portable computer, and no one refined it more masterfully than the astronomer Al-Battani. Working from his observatory in Syria, he did not just use the Astrolabe, he re-engineered it, introducing more precise scales and creating new trigonometric tables that transformed it from a useful tool into a device of stunning accuracy. Historian David A. King points out that these improvements allowed scholars to determine the exact time of night by the stars, calculate the direction to Mecca for prayer, and predict the movements of celestial bodies with a reliability never before achieved. The Astrolabe was a beautiful fusion of art and science, a symbol of a culture where astronomical knowledge was woven into the fabric of daily life and spiritual practice. To use one, you would suspend it by a ring, allowing the pierced fretwork of the top plate, called the reter, to rotate over an engraved plate known as the mater. The reter was a star map, its pointers marking key stellar positions, while the mater beneath it was a coordinate grid for a specific latitude. By aligning the reter with the observed sky, you could solve dozens of practical problems, from telling time to charting a course. There were planar astrolabes for general use and more complex spherical versions that modeled the heavens in 3 dimensions. For centuries, this instrument was the pinnacle of navigational technology, guiding travelers across deserts and oceans by connecting their earthly journey directly to the stars above. Yet, the very turmoil that eventually fractured the Islamic empires also consumed these masterpieces. The original, personal astrolabes of great thinkers like Al-Battani were lost to looters, melted down for their metal, or simply crumbled into dust, their precise calibrations forgotten. His detailed written work survived to inspire Renaissance astronomers in Europe, but the physical instruments themselves were gone. It makes you wonder if every ship setting out during the Age of Exploration had been equipped with an astrolabe refined to Al-Battani's standards, how many failed voyages might have succeeded? How much sooner would new continents have been mapped? The loss of these artifacts is a stark reminder that scientific progress depends not just on ideas, but on the fragile physical objects that embody them. This intimate link between observing the heavens and measuring time would find its ultimate medieval expression in a device that was both a clock and a cosmic model. Time itself flowed like a river in the workshops of Ctesibius, and he sought to build a container for its endless current. In 3rd century BC Alexandria, this brilliant inventor perfected the clepsydra, or water clock, transforming it from a simple timer into a sophisticated astronomical instrument. These were not just devices for counting the hours of the night. They were complex machines that tracked the long, slow dance of the heavens. Ctesibius engineered his most advanced models with a series of gears and turning dials that displayed the shifting positions of the planets, effectively creating the world's first automated planetariums for scholarly study. Imagine a towering structure of reservoirs and siphons, where the steady drip of water powered a miniature cosmos. classicist James Evans notes the true genius was in the feedback mechanisms Ctesibius designed to maintain a constant water pressure. He used a float valve, similar in principle to the one in a modern toilet tank, to automatically regulate the flow into the timing chamber. This ensured the clock did not speed up as its main reservoir emptied, a problem that had plagued earlier designs. This was not just a timekeeping innovation, it was a precursor to the principles of automation and control engineering that would take millennia to fully re-emerge. Within observatories, these clocks provided the consistent time base needed to make precise measurements, such as timing the exact moment a star crossed the meridian or predicting the start of an eclipse. Some elaborate versions even featured automated figures that would rise to mark the hour or move in sync with celestial events, a breathtaking fusion of engineering and art. The reasons these marvels vanished are as material as they are tragic. Their intricate gears were made of wood that rotted away, their water channels silted up, and their bronze components were likely scavenged and melted down for other purposes. The final death knell for this knowledge was the destruction of the great libraries and workshops that housed their designs, leaving only descriptions in surviving texts by other writers. Modern engineers who have attempted reconstructions based on these ancient accounts are consistently amazed. They have built working models that can accurately simulate the phases of the moon or the movements of the sun, proving the theoretical sophistication was matched by practical, mechanical genius. How different would our history be if we had enjoyed 2,000 years of continuous, automated celestial observation? The disappearance of Ctesibius's water clocks meant a profound setback, a dark age for mechanical computation that forced humanity to start over. Yet the ghost of his principle, using one regulated natural force to measure another, echoes in every digital planetarium that projects a perfect, moving sky today. This desire to capture the cosmos in a tangible form would soon find expression not in flowing water, but in frozen glass. Deep inside the royal workshops of Al-Andalus, artisans breathed stars into glass. They crafted hollow spheres perfectly transparent, and on the inner surface, they carefully engraved the constellations in silver and gold. To look upon one of these glass celestial globes was an experience unlike any other. You were not looking at a map of the sky, you were inside the cosmos itself, gazing outward at the stars from the imagined center of the universe. Produced from the 10th to the 12th centuries in Islamic Spain, these globes represented a revolutionary shift in perspective. They transformed the celestial sphere from an abstract concept into a tangible, immersive reality. Art historian Sabiha Gurluglu notes that the beauty of these objects was inseparable from their function. The constellations were often labeled with elegant Arabic calligraphy, turning each globe into a masterpiece of both science and art, a portable universe that fit in the palm of your hand. The manufacturing process was a marvel of its own, requiring master glassblowers to form a perfect hollow sphere, and then skilled engravers to work from the outside, painstakingly etching the star patterns in reverse so they would appear correctly when viewed from within. These globes were often accompanied by detailed treatises explaining their use for both education and navigation. In the madrasas, students could hold the universe and rotate it in their hands, physically grasping the apparent daily motion of the stars and the paths of the planets along the ecliptic. For a traveler, the globe could be used to identify prominent stars visible on a journey, a practical guide written in light and glass, but their very nature made them vulnerable. The invasions that reconfigured the Iberian Peninsula brought chaos that shattered these delicate worlds. The glass, so beautiful and transparent, was also incredibly fragile, susceptible to a single drop or the crush of conflict. Almost none survive today, How might our innate sense of the cosmos be different if every child learned astronomy not from a flat screen or a paper chart, but from holding a miniature, glittering universe in their own two hands? The loss of these glass globes is a poignant lesson in how material fragility can erase entire chapters of our intellectual history. This delicate fusion of cosmic knowledge and crafted material would find a far more durable, yet equally unexpected, expression in the next artifact, where the secrets of the stars were woven not into glass but into textiles. High in the thin air of the Andes, a priest's fingers moved with practiced grace, tying knots into a cascade of colored cords. Each loop and twist was a silent word, a record of the night skies turning. This was the Quipu, the Inca Empire's extraordinary memory device, and it held the secrets of the stars. Far more than simple accounting tools, certain Quipu were dedicated astronomical calendars, encoding the rhythms of the cosmos into a language of string. The arrival of solstices, the cyclical return of the Pleiades cluster, known as Quulcar or the storehouse, and the movements of planets were all meticulously recorded. The appearance of this star group on the horizon signaled the start of the planting season, weaving celestial events directly into the survival of a civilization. Anthropologist Gary Urton has proposed that the system was profoundly sophisticated, with the colors of the chords, the direction of the spins, the types of knots, and their precise positions all forming a structured, almost binary code for storing complex information. Imagine a Quipu where a red string represented Mars, and the sequence of knots along its length plotted its retrograde motion against the fixed stars. Another set of chords, perhaps in the deep blue of the night sky, could chart the 18-month synodic cycle of Venus. The numerical data encoded in these knots allowed priests to predict eclipses and maintain a calendar of exceptional accuracy, governing everything from religious festivals to the agricultural year. The Spanish conquistadors who arrived in the 16th century saw only pagan idols in these intricate textiles. In their campaign to extinguish native culture, they systematically gathered and destroyed countless Quipu, burning them as works of the devil. This was not merely the loss of objects, but the silencing of an entire library. The specialized astronomical Quipu, with their unique color codes and complex knot sequences, were wiped from existence, taking with them a complete system of indigenous cosmic wisdom. Today, researchers use computer algorithms to analyze the few hundred surviving Quipu, searching for mathematical patterns that might correlate with known celestial cycles. The results are tantalizing but incomplete, like hearing a few scattered notes from a symphony that has been lost forever. How would our understanding of the southern sky be different if we could read the star lore locked within those threads? The Quipu's destruction represents a profound cultural amnesia, a severed connection to a way of seeing the universe that was both practical and deeply spiritual. This drive to mechanize the heavens, to build machines that could mirror the cosmos, would soon find its voice in a different kind of wonder, one that sang the time in a chorus of bells and gears. In the torchlit atrium of a Roman villa, a nobleman gathered his guests around a small, intricate machine. With a turn of a crank, bronze spheres began their silent dance, tracing perfect circles around a central orb of gold. This was a mechanical orrery, a miniature cosmos powered by human hands. While we often credit these devices to 18th century Europe, their origins reach back into the classical world. The orator Cicero himself wrote of a similar sphere built by the philosopher Posidonius, a device that showed the movements of the sun, the moon, and the 5 known planets with each turn of its handle. For the Roman elite, such an object was more than a curiosity. It was a powerful status symbol and a tool for philosophical demonstration. It illustrated an orderly, predictable universe, a concept central to the Stoic beliefs popular among the educated class. Historian Michael Wright points out that while no complete Roman orrery survives, the technological capability was certainly there. Roman engineers, having access to Greek texts and mechanical principles, were masters of gearing, as seen in their water mills and complex siege engines. They would have possessed the skill to craft such planetary models from bronze and wood. The true genius of these early orreries was their ability to visualize complex celestial phenomena. A guest watching the model could witness the planet Mars slow down, reverse its course in a graceful loop, and then resume its forward motion against the backdrop of fixed stars. This was retrograde motion, a baffling celestial event perfectly explained by the simple, mechanical interplay of gears. It demystified the heavens, making the grand clockwork of the cosmos accessible to anyone present. Archaeological finds, like the unassuming gear fragments from Roman shipwrecks or settlements, hint at this lost complexity. They are not labeled, but their tooth profiles and calculated ratios suggest they could have been part of devices far more ambitious than simple clocks. Modern museums have used these clues to build working reconstructions, proving that the theoretical knowledge for such planetariums existed centuries before we thought possible. How many minds were first ignited by seeing the solar system set in motion on a tabletop? The loss of these Roman orreries, likely melted down for their valuable bronze or simply rotted away, created a profound gap in the history of public science. It severed a direct, tangible link between ordinary people and the mechanics of the heavens, a connection that would take over 1,000 years to reforge. This desire to make the cosmos comprehensible would soon find expression in an artifact that used not gears, but pure light to reveal the secrets of the stars. Light itself became the painter, tracing perfect, inverted images of the heavens onto a darkened wall. In the 11th century, the brilliant scholar Ibn al-Haytham turned a simple principle into a revolutionary astronomical instrument, the Camera Obscura. He demonstrated that light travels in straight lines by constructing a dark chamber, or even a simple box, with only a tiny pinhole open to the outside world. The scene outside, including the sun or the moon, would be projected inside, upside down but in perfect, shimmering detail. For the first time, astronomers could study the sun safely. They could observe a solar eclipse in its entirety without risking blindness, watching the moon's shadow crawl across the sun's brilliant disk as a dim, cool image on the wall. They could analyze the phases of the moon and even track the rough outlines of sunspots, those blemishes on the face of our star. Physicist Jim Al-Colally often highlights how al-Haytham's rigorous experiments with this device fundamentally debunked the ancient Greek idea that vision worked by rays emitted from the eye. He proved we see because light enters the eye, a foundational shift in our understanding of optics. Yet the original, dedicated astronomical camera obscuras he built, likely elaborate structures in Basra or Cairo, were lost to time, their specific designs fading into obscurity. The principle, however, was too powerful to disappear entirely. The device evolved from fixed rooms into portable, tent-like versions, and later small boxes that artists and scientists could carry into the field. Translations of al-Haytham's Book of Optics spread to Europe, where it influenced minds like Leonardo da Vinci, who used the camera obscura to study perspective and light. Medieval texts describe astronomers using these projections to meticulously map the irregular edges of a solar eclipse, gathering data that prefigured our modern understanding of the sun's corona and the moon's topography. How many more secrets of the sun might we have unlocked centuries earlier if every medieval observatory had been equipped with a permanent camera obscura? The loss of these specialized setups is a quiet lesson in how the simplest ideas, when lost, can delay a revolution. This profound understanding of light and shadow, of capturing an image of the cosmos, would find a far more permanent and public expression in the next artifact, where cosmic knowledge was not projected fleetingly on a wall, but carved for eternity into stone. Deep in the jungles of Central America, 19th-century archaeologists brushed away centuries of vine and soil to reveal towering stone monuments. These were the Mayan Stelae, and their carved surfaces held a language of time itself. Far more than mere markers of kings, these stone pillars were public archives of the cosmic order, their inscriptions recording the movements of planets and stars with breathtaking precision. Epigraphers like David Stewart have dedicated their lives to deciphering the intricate glyphs, revealing a system where a ruler's divine right to rule was directly tied to celestial events. A king's coronation scheduled to coincide with the rising of Venus, or a military victory celebrated under a specific lunar phase, demonstrated his harmony with the heavens. The Maya used a base 20 numerical system, a vigesimal count, to plot these events across immense spans of time. Their most famous creation, the long count calendar, carved onto stelae like the one at Quirigua, tracked cycles of over 5,000 years. This was not an abstract fascination. It was the practical rhythm of life, predicting seasonal rains for planting maize and organizing the entire agricultural year around the reliable clockwork of the sky. The materials themselves tell a story of fragility amidst permanence. Most stelae were carved from limestone, which slowly dissolves in the humid tropical rains, while a precious few were made of wood, which succumbed to rot and insects. The Spanish conquest accelerated this loss, with missionaries toppling and defacing many monuments, seeing their celestial glyphs as pagan idolatry. At sites like Capon, specific stelae were erected to align with the setting points of star clusters like the Pleiades, events that would be illuminated during certain festivals, turning the entire city into a vast astronomical observatory. What advanced knowledge of celestial mechanics, what predictions of comet cycles or supernova have been washed away by the tropical storms? If these stone libraries had remained fully legible, how might their long-term tracking of planetary cycles have accelerated our own understanding of orbital dynamics? The erosion of the Mayan stelae is a slow-motion silencing of a brilliant astronomical tradition. This profound connection between cosmic patterns and human perception would soon find expression in an artifact that translated the visual heavens into an entirely different language, the language of sound. A priest in ancient Babylon squints at the evening sky, his stylus poised over a damp clay tablet. He is not merely observing, he is decoding a divine message. For every flicker of Jupiter or slow retreat of Mars is an omen from the gods. These Babylonian celestial omens, inscribed in meticulous cuneiform on tablets dating back to the first millennium BCE, represent a breathtaking fusion of science and superstition. They formed the Enuma Anu Enlil series, a massive, multi-tablet encyclopedia of the sky that linked celestial events directly to the fate of the kingdom. A lunar eclipse might foretell the death of a king, the appearance of Venus could signal a coming war, and the retrograde motion of Jupiter was seen as a direct blessing upon the ruler. Assyriologist Francesca Rochberg emphasizes that while these interpretations were divinatory, the methods were profoundly empirical. The priests were not guessing, they were recording, amassing centuries of precise, naked-eye observations that allowed them to identify complex cycles. They could predict the appearances and disappearances of Venus with remarkable accuracy, and understood the repeating patterns of lunar eclipses within a cycle known as the Saros. This was not magic, it was data science etched in clay. The very material of these tablets, baked hard in the sun or kilns, was chosen for permanence, meant to preserve this celestial knowledge for generations. Yet this durability could not protect them from everything. The great library of Nineveh, a treasure trove of these omen texts, was burned and shattered by invaders, its clay tablets fractured and scattered. Countless others simply crumbled back into the earth from which they were made, their precise mathematical sequences lost forever. We have recovered fragments that show the Babylonians calculating the motion of Jupiter using geometric methods that prefigure calculus, a conceptual leap of staggering genius. How many other mathematical insights, what deeper understandings of planetary motion, were written on the tablets that did not survive? This systematic recording of the heavens provided the raw data that would later fuel Greek and Indian astronomy, forming the very bedrock of Western science. The loss of so many of these clay records created gaps in our cosmic memory, a forgotten chapter where the line between prophecy and prediction was beautifully, brilliantly blurred. This drive to carry the cosmos, to make it personal and portable, would soon manifest in an artifact that fit in the palm of your hand. In the hushed stillness of a medieval scriptorium, a monk's knife carefully carved a circle from a sheet of parchment. This was no mere illustration, it was a working machine made of paper, a volvelle. With layered discs that rotated on a central thread, these intricate paper instruments turned sacred manuscripts into interactive analog computers. By aligning a dial marked with zodiac signs against another showing lunar phases, a scholar could calculate the ever-shifting date of Easter or determine the planetary hour for prayer and medical procedures. They modeled the cosmos with a turn of the wrist, making complex astronomical problems tangible for the clergy, students, and even navigators. Book historian Faith Wallace explains that volvelles were a revolutionary form of knowledge technology. They democratized celestial calculation. You did not need a grand brass astrolabe or a wealthy patron. You needed only a carefully crafted book. The design was a marvel of paper engineering. The base layer might show a star chart. A second disk could represent the sun's annual path along the ecliptic, and a third, perhaps a delicate pointer, would be tied on with a silk thread. By rotating these components, a user could solve for the position of the moon or even predict an eclipse. The craftsmanship was meticulous, with hand-painted illustrations and precisely cut tabs ensuring smooth operation. These were not just tools, they were beautiful objects, a fusion of art, faith, and science bound between two covers, yet their material was their ultimate weakness. Parchment is fragile, susceptible to damp, fire, and the simple wear of eager fingers turning the disc century after century. Countless volvelles were lost as manuscripts were dismantled for their bindings or simply crumbled into dust. Many that survive are so delicate that museum curators dare not operate them. We know their power from reconstructions based on texts like Johannes de Sacrobosco's Sphere, a standard astronomy textbook that used these paper devices to teach spherical astronomy to generations of students. Can you feel the difference between reading about the moon's cycle and physically moving a dial to see it unfold before your eyes? Interactive learning sparks a deeper, more intuitive understanding, a connection that static text alone can never achieve. The decay of these medieval volvelles is a quiet tragedy of ephemeral media, a reminder that some of our most brilliant ideas are written on the most perishable of materials. This desire to build machines that could read the wind and the stars would soon find its ultimate expression in a colossal observatory that used nothing but stone and air. A silent desert wind once turned stone into a precision instrument. In ancient Persia, master architects harnessed this invisible river of air to build observatories that breathed with the sky itself. During the Sasanian era, structures like the possible observatory at the Academy of Gundashapur were engineered not just for observation, but for stability. They featured tall towers with carefully placed openings aligned to the prevailing winds, creating a constant, gentle airflow through the interior. This was not for comfort, but for science. By channeling the wind, these buildings reduced the heat shimmer and air turbulence that can make stars twinkle and dance, distorting the view for naked-eye astronomers. It was a form of ancient air conditioning, creating a clearer window to the cosmos for the quadrants and astrolabes housed within. Historian Turaj Darii points out that this architectural genius was deeply intertwined with Zoroastrian beliefs, where the celestial spheres were considered a realm of perfect purity and order. Reducing the atmospheric interference was a way to get closer to that divine perfection, to see the heavens as they truly were. This stable environment allowed for the long-term, patient monitoring required to track the slow drift of planets and compile detailed star catalogues. Historical accounts describe Persian astronomers using these calm vantage points to record the sudden appearance of comets and the fixed positions of distant stars, data that directly informed crucial reforms of the solar calendar. Can you envision an alternate history of astronomy, where every major observatory was built with this kind of sustainable, passive cooling? How much more precise might our early star maps have been if this architectural philosophy had become the global standard? The loss of these sites to Mongol invasions and devastating earthquakes is more than just the loss of buildings. It represents a severed thread in the story of eco-friendly science. This elegant fusion of natural forces and human observation finds a stark contrast in the next artifact, where the quest for cosmic clarity turned from harnessing the wind to manipulating light with mirrors. A polished bronze disc curved to a perfect parabola could catch the moonlight and focus it into a brilliant, magnified image. This was the speculum, the mirror at the heart of a revolution that never quite happened. Centuries before Isaac Newton, the brilliant Ibn al-Haytham, known in the West as Al-Haytham, was not just projecting images with his camera obscura, he was experimenting with curved mirrors. In his legendary book of optics, he described how these specula, meticulously ground from bronze or even silver, could gather and reflect light to enlarge distant objects. He was pioneering the very principles of the reflecting telescope, crafting prototypes that could have turned the heavens into a detailed map. Imagine an 11th century astronomer in Cairo, peering into a speculum mounted in a dark tube, seeing the craters of the moon not as a fuzzy glow, but as a landscape of stark shadows and sharp peaks. These metal mirrors could have revealed the phases of Venus, resolving it from a mere point of light into a delicate crescent, and perhaps with enough precision, even spotted the 4 largest moons of Jupiter dancing around their giant host. Historian Richard Lorch notes that Al-Haytham's rigorous work on reflection and refraction provided the entire theoretical bedrock for later telescopic science. He understood spherical aberration, the distortion caused by simple curved mirrors, and his writings suggest he was grappling with the mathematics needed to create a perfect parabolic shape that would bring all light to a single, sharp focus. The grinding process itself was an art, requiring days of patient polishing with fine abrasives to achieve that critical curve without a single flaw. Yet, no original specula from his workshops survive. The metals were too valuable, likely melted down and repurposed over the centuries. The delicate mirrors tarnished and corroded in the humid air, their brilliant surfaces growing dull and useless. The knowledge of how to grind them was preserved in texts, but the physical prototypes, the proof of concept instruments, were lost. Modern opticians have followed his descriptions to build working replicas, and the results are startlingly clear. With a speculum of the quality Al-Haytham could theoretically have produced, the Galilean moons of Jupiter are unmistakable. What if his reflective telescopes had become standard equipment in every medieval Islamic observatory? the discovery that Jupiter had its own system of moons, a solar system in miniature, might have occurred 400 years before Galileo, fundamentally reshaping our place in the universe almost overnight. The absence of al-Haytham's specula is a haunting testament to a road not taken, a brilliant branch of astronomy that remained a theoretical twig because the physical tools decayed. This loss reminds us that a brilliant idea needs a durable body to change the world, and sometimes that body is not a tool of metal or glass, but a sequence of notes, a cosmic harmony translated into sound. The universe hums a silent melody, a mathematical music the ancient Greeks believed only the privileged could hear. Pythagoras and his followers envisioned the cosmos not as a void, but as a grand, resonating instrument, its structure defined by harmonic spheres. Each planet, as it moved through its orbit, was thought to produce a distinct musical note, the combination forming a celestial symphony known as the music of the spheres. This was not a physical artifact you could hold, but a conceptual one of breathtaking ambition, an attempt to unify the laws of physics with the principles of beauty through pure mathematics. Historian Reveal Netz points out that the Pythagoreans used precise mathematical ratios, the same ones that govern the lengths of a vibrating string, to relate the sizes and distances of the planetary orbits to musical intervals. They imagined the moon's sphere produced one note, the sun's sphere another, creating a cosmic scale that played a continuous, ethereal chord. For them, the order of the universe was literally harmonious. This idea wove itself deeply into Western cosmology, influencing thinkers for 2,000 years. The original diagrams and texts that detailed these proportions, however, were casualties of a changing intellectual world. As Neoplatonic schools declined and classical libraries were dispersed, the nuanced teachings on cosmic harmonics were fragmented and simplified, their profound mathematical core often reduced to a poetic metaphor. The most direct legacy of this lost concept appears in the work of Johannes Kepler. Even as he discovered the elliptical orbits of the planets, he was still searching for their hidden music. In his work Harmonices Mundi, he assigned specific musical notes to each planet based on its orbital speed, creating a melody for the solar system that was, for the first time, grounded in observational data. Modern scientists have used software to simulate these Pythagorean and Keplerian scales, translating orbital ratios into sound waves we can actually hear. The result is a sequence of otherworldly chimes and drones, a haunting echo of an ancient intuition. Does the fact that we can now listen to a mathematical model of the solar system make the idea any less profound? The loss of the original harmonic theory left a poetic void in astronomy, a reminder that our drive to understand the cosmos is as much about finding beauty as it is about finding facts. This search for meaning in the heavens would soon take a dramatic turn, as another civilization sought to read the stars not through sound, but through the primal element of fire. A single thread of fragrant smoke curled upward into the cold night air, a silent metronome for the turning stars. In the imperial observatories of Tang Dynasty China, astronomers relied on incense clocks where time itself was measured in scent and ash. These were not simple sticks of incense but intricate tools of science. Master horologists had calibrated specific powders, blending sandalwood, aloes wood, and other fragrant materials to burn at a perfectly steady, predictable rate. An astronomer on the night watch would light a long, specially prepared coil or a patterned trail of powder laid out in a groove. As the glowing ember progressed, its distinctive fragrance would shift at predetermined intervals, signaling the passage of time without the observer ever needing to look away from the sky. Joseph Needham's research into these devices reveals a system of remarkable sophistication. Different scents could mark the quarters of an hour, allowing a scholar to note the exact moment a star vanished behind the moon's dark limb, or to time the duration of a meteor shower's peak activity. This provided the consistent, long-term data needed to track the subtle brightness changes of variable stars, a task nearly impossible with unreliable water clocks on a frosty night. The construction was an art form. Some clocks were maze-like patterns engraved on bronze plates, while others were long, coiled ropes of incense that could burn for 12 hours or more. In the most advanced systems, the ash itself became part of the record. The position of the burning tip along a calibrated scale could be directly correlated with a star's altitude on a corresponding chart, creating a direct physical link between the scent in the air and a coordinate in the heavens. Historical texts describe how these clocks were essential for logging lunar occultations, events where the moon passes in front of a star. The precise timing of these disappearances and reappearances, recorded via the incense's progress, provided critical data for refining the imperial calendar to an astonishing degree of accuracy. Can you sense the difference between this ancient practice and our modern digital timers? To spend a night under the stars, guided by the rhythms of fragrance, connected the cosmos to the Earth in a deeply sensory way. The experience was not just numerical, it was holistic, engaging smell and sight in a unified act of measurement. The eventual displacement of these incense clocks by mechanical timepieces from the West led to the complete loss of their specific design. The recipes for the calibrated powders, the precise patterns of the grooves, all of it faded away because the materials were inherently perishable. This disappearance represents more than the loss of a tool. It signifies a forgotten philosophy where time was a continuous, sensory flow, intimately woven into the fabric of the night. This integration of cosmic observation into the objects of daily life would find a surprising parallel in an artifact that was both a household item and a window to the heavens. A blanket of stars was woven into the very homes of the Navajo people. Inside the traditional dome-shaped hogan, the ceiling became a perfect, intimate sky, painted with constellations using natural pigments of red ochre, charcoal black, and white clay. This was not mere decoration, it was a sacred classroom where elders passed celestial knowledge to the young, ensuring the stars would forever guide their community. The patterns were deliberate, mapping key constellations like the Pleiades, known as Stelae, Heng, or the cluster that is a source of seeds, and the strong central figure of first big one, which many recognize as Orion. Each star group held a story, a piece of a creation narrative that connected the people to the cosmos in a relationship of reverence and responsibility. Ethnographer Trudy Griffin Pierce noted that these star ceilings encoded vital, practical information. The rising of Stelae Heng in the evening sky signaled the start of the winter stories, a time for teaching and reflection, while other star paths marked the proper seasons for planting corn and for holding specific healing ceremonies. On long winter nights, a family would gather inside the hogan, the central fire casting flickering shadows that brought the painted constellations to life. An elder would point to a specific pattern, using a corn pollen offering to trace its path, and recite the stories and lessons bound to that part of the heavens. The knowledge was not written down, it was lived and breathed within the very structure of the home, a perfect fusion of spiritual belief and observational science. The materials themselves, however, were vulnerable. The hogans were built from wood and packed earth, and the pigments, while beautiful, would fade over time or be washed away by rain seeping through the roof. As colonization pushed modernization and traditional ways were suppressed, many of these star-painted hogans were abandoned, left to collapse back into the earth. The specific meanings of some patterns were lost as elders passed away without someone to whom they could entrust the full knowledge. Can you feel the profound difference between learning astronomy from a book and being taught the stars while lying beneath them, painted on the ceiling of your own home, your family's voices weaving the tales? This was a science of deep personal connection, an astronomical heritage that was literally part of the household. The fading of the Navajo star ceilings is a quiet erosion of an entire worldview, a reminder that some of our most profound cosmic maps were written not on paper, but on the walls of memory and home. This intimate dance of light and knowledge finds a stark contrast in the next artifact, where the goal was not to paint the stars, but to capture the sun's own shadow with absolute precision. The shadow of a granite obelisk stretched across the sun-baked plaza, a dark finger tracing the sun's daily journey. Egyptian pharaohs erected these towering gnomons not merely as monuments to their power, but as colossal scientific instruments. From the Old Kingdom onward, these sharp-tipped obelisks served as giant, immovable sundials, their moving shadows allowing temple priests to track time with remarkable accuracy and to pinpoint the critical moments of the solar year. The key to their power was the precise measurement of that shadow's length and its direction. At noon, when the sun reached its highest point, the shadow was at its shortest. By recording the shortest shadow length each day, priests could identify the summer solstice, the day it was briefest, and the winter solstice, the day it stretched longest across the ground. The 2 days each year when the shadow's path was perfectly straight, dividing day and night equally, marked the equinoxes. This was not just about telling time, it was about building a calendar that synchronized human activity with the cosmos. Egyptologist Marshall Claggett explains that the placement of these obelisks was an act of encoded geometric knowledge. They were often positioned to align with the heliacal rising of Sirius, the event where the star first becomes visible just before dawn after a period of invisibility. This celestial event, which coincided with the annual flooding of the Nile, was the true new year for ancient Egypt, a direct link between a star, a river, and the survival of a civilization. At temple complexes like Karnak, the obelisk's shadow would fall upon specific markers during festivals, turning the entire architecture into a cosmic clock that dictated religious and agricultural life. The effort to create these tools was Herculean. Quarried from single blocks of red granite or limestone, each obelisk was a masterpiece of logistics, transported on barges and raised into position with ramps and ropes, all to capture a sliver of darkness. The data gathered from centuries of watching these shadows provided the ancient world with profound insights into Earth's axial tilt and the sun's cyclical path, knowledge that would later travel to Greece and form the basis of their own astronomical studies. It is a powerful reminder that a simple stick in the ground, if observed with patience and rigor, can reveal the fundamental rhythms of a planet. Many of these original obelisks were looted, toppled by invaders, or moved to distant city squares in Rome and Istanbul, where their carefully calibrated alignments were lost, their primary function as astronomical tools forgotten beneath their new role as trophies. This ancient dance of light and shadow, using a solid object to measure the sun, finds a strange parallel in our next artifact, which sought to model the cosmos not with stone, but with the ever-changing flow of liquids. A theater stage in 1st century Alexandria came alive not with actors, but with the silent, fluid motion of the cosmos itself. The engineer hero amazed audiences with his automated theaters, where complex water-powered mechanisms set celestial spheres spinning in a mesmerizing dance. These were his hydraulic models, intricate devices described in works like Pneumatica that transformed abstract Greek cosmology into a public spectacle. Water flowing through a series of siphons and gears would drive spheres representing the sun, the moon, and the known planets across a model sky, illustrating complex ideas like epicils long before Ptolemy formalized them. Engineer Barry van Berkel notes these models were not just toys, they were profound educational tools, precursors to the mechanical orreries that would captivate Europe centuries later. The principles were a masterful application of basic physics. Water pressure and the displacement of air within sealed vessels provided the steady force needed to turn gear trains, moving the planets along their paths at different calibrated speeds. Valves and adjustable flow rates meant a single device could be reconfigured to demonstrate various planetary alignments or the timing of an eclipse, all powered by nothing more than gravity and the relentless drip of water. These shows were a hallmark of Hellenistic science, where wonder was a gateway to understanding, and complex astronomical concepts were made tangible for everyone. Yet not a single complete hydraulic model survives. The pipes corroded, the wooden gears rotted, and the papyrus scrolls detailing their construction were lost to fire, decay, or simply the slow neglect of a changing world. Modern reconstructions based on Hero's texts are a revelation. Watching a planet glide through a retrograde loop, driven by nothing but water, makes the clockwork of the heavens feel immediate and graspable. Does this ancient fusion of entertainment and education remind you of a modern science museum planetarium show? The drive to make the cosmos interactive is clearly not new. The disappearance of Hero's hydraulic artifacts left a gap in our mechanical heritage, a lost chapter in public astronomy. This desire to map the heavens on a lasting surface would soon find expression in an artifact that traded flowing water for the stretched skin of an animal. The scratch of a quill was the only sound in the cold scriptorium, a monk's numb fingers tracing the curve of Draco onto a page of prepared vellum. In the flickering candlelight, he was not merely drawing, he was building an ark for knowledge, preserving the classical stars through Europe's so-called Dark Ages. These parchment star charts, often bound into hefty astronomical codices, transformed animal skin into a window to the cosmos. They depicted the constellations in rich black ink and shimmering gold leaf, their designs painstakingly copied from sources like Ptolemy's Almagest that had survived the fall of Rome. For the monastery, these were not just beautiful objects, they were vital tools. They helped determine the correct dates for movable feasts like Easter, guided the nocturnal prayers of the canonical hours, and even offered rough navigation for the rare traveler. Paleographer Bruce Eastwood's research confirms that monasteries like Reichenau and Fulda became unexpected hubs for celestial study, where the rhythm of the liturgical year was synchronized with the clockwork of the heavens. Yet for every chart that survived, countless others were lost. The very material that preserved them also doomed them. Parchment is hygroscopic. It drinks moisture from the air, becoming a breeding ground for mold in damp cloisters. Bookworms, the larvae of insects, tunneled through the star fields, leaving behind a trail of destruction as they ate. Some manuscripts were scraped clean and written over, their celestial maps erased to make room for new texts, a process known as palimpsesting. Others were lost to the all-too-common monastery fires, their knowledge turning to ash in an instant. The production of a single chart was an act of immense devotion. It began with soaking and stretching an animal skin, scraping it thin with a lunellum knife, and then polishing the surface to a smooth finish. Using a sharp stylus, the monk would score faint grid lines for celestial coordinates before beginning the intricate work of inking the constellations, often adding their mythic forms from Greek legend. The resulting maps were hybrids of ancient knowledge and medieval interpretation, sometimes featuring Arabic star names like Betelgeuse and Aldebaran that had filtered into Europe through translated texts, a silent testament to a forgotten era of cultural exchange. One of the rare, nearly intact survivors is the St. Gallen planisphere, a stunning map that served as a visual textbook for monastic education. Its precise arrangement of stars, copied from a much older source, reveals a medieval understanding of the sky that was far more accurate than we often assume. Can you feel the weight of that responsibility? The immense labor required to ensure that a single thread of cosmic knowledge was not broken. The slow fragmentation of these parchment charts created missing links in our star mapping tradition, gaps in the celestial record that forced astronomers of the Renaissance to rediscover what had already been known. This fragile preservation of light finds a dramatic contrast in the next artifact, where the goal was not to draw the sun, but to observe it directly through the heart of a crystal. A Norse longship cut through the North Atlantic fog, its sail limp in the still air. With the sun completely hidden for days, the navigator held a translucent crystal up to the overcast sky, turning it slowly until a faint, telltale pattern emerged. This was the legendary Sunstone, a Viking artifact of pure practicality that turned the entire sky into a compass. Sagas like the saga of King Olaf mention these stones as vital tools for finding the sun on cloud-shrouded days, a skill that meant the difference between reaching a new shore and vanishing into the gray expanse. Archaeologists like Gabor Horvath have tested crystals native to Scandinavia, such as calcite and cordierite, and found they can pinpoint the sun's position with an accuracy of just a few degrees, even when it is completely below the horizon. The secret lies in a property called birefringence. These crystals split incoming light into two separate rays. By looking through the stone and rotating it, a skilled user would see two glowing spots or a distinct dark band appear when the crystal was aligned with the hidden sun's position, revealing its direction through the polarized light patterns scattered by the atmosphere. This technique gave Viking explorers a crucial edge in northern latitudes, where overcast skies were the norm and the magnetic compass had not yet arrived from the south. They were navigating by reading the very fabric of the light itself. The types of stones used were not rare jewels but clear, well-formed pieces of Iceland spar or transparent cordierite, often carried in a small leather pouch or set into a wooden handle. This is precisely why no definitive sunstone has ever been found in a Viking grave or settlement. They were small, organic, and looked like unremarkable pebbles, easily lost, discarded, or simply not recognized by modern excavators. Their loss is a perfect example of how an entire technology can vanish without a material trace, leaving only echoes in old stories. Modern sailors have used replica sunstones to successfully navigate replica voyages, proving the concept works with stunning reliability. How much further might this knowledge have spread if it had been written down and shared beyond the Norse world? Could it have changed the course of exploration for other seafaring cultures? The sunstone's disappearance is a ghost in the archaeological record, a brilliant solution to a celestial problem that faded away with the last navigator who knew its secret. This fusion of earthly material and celestial guidance finds a strange parallel in the next artifact, where the quest was not to find the sun, but to transform base metal into a model of the cosmos itself. A crucible of molten metal held the light of a distant planet. This was the world of Paracelsus, where 16th century alchemy and astronomy were not separate disciplines, but two languages describing the same cosmic truth. His alchemical astrolabes were masterpieces of this fusion, transforming the common navigational instrument into a key for unlocking the hidden influences of the heavens. These were not for finding north or telling time, but for determining the precise celestial moment to begin a distillation or to combine reagents, based on the belief that planetary alignments directly affected material transformations. Historian Lawrence Principe emphasizes that Paracelsus saw the universe as a single, living entity, a macrocosm reflected in the microcosm of the human body and the laboratory flask. His astrolabes were unique because they integrated Hermetic philosophy directly into their design, encoding a worldview where the stars above and the metals below were in constant, sympathetic conversation. The design of these instruments was radically different from their standard counterparts. They featured additional dials and plates engraved not just with stars, but with the symbols for the 7 classical planets, the 12 zodiac signs, and the 4 Aristotelian elements. A master alchemist would use this device to calculate the planetary hour, a time period ruled by a specific celestial body, and then cross-reference it with the sign the moon was occupying. This complex calculation would tell him the most auspicious moment to begin the process of creating a particular medicine or attempting a metallic transmutation. The materials themselves were part of the magic. Crafted from brass, a metal associated with Venus, the astrolabes were often covered in intricate esoteric motifs, from Ouroboros serpents to geometric seals, turning the tool into a talisman as much as a calculator. Surviving manuscripts describe practitioners using these astrolabes to guide the creation of laudanum or to determine the exact phase of the moon for planting the herbs used in their experiments. This was astronomy permeating the most practical aspects of daily life and health. Can you see the innovative spark in this interdisciplinary approach, even if we no longer believe in planetary influences on chemistry? It was a system that sought patterns and connections in a universe it believed was fundamentally interconnected. The loss of most alchemical astrolabes was systematic. The rise of the scientific revolution actively marginalized alchemy, viewing it as a superstitious relic. Many instruments were deliberately destroyed or melted down to avoid persecution, while others were simply discarded as their secretive owners passed away without heirs to their knowledge. This dispersal broke a chain of thought that saw the cosmos and the laboratory as one. The disappearance of Paracelsus's instruments represents a forgotten synergy, a road where cosmic curiosity and chemical experiment walked hand in hand. This intricate dance of measurement and meaning finds a simpler, yet equally profound, expression in an artifact that used nothing more than knotted strings to chart the heavens. A priest in the cool desert night waits, a forked stick and a dangling plumb line his only tools. With this simple merkit, ancient Egyptians charted the heavens with a precision that still defies belief. Since the Old Kingdom, this instrument, a horizontal palm rib with a weighted string suspended from its center, was the key to aligning their world with the cosmos. A second priest would stand a precise distance away, his own merkit raised. Together, they would watch a chosen star, like the imperishable circumpolar ones that never set, waiting for it to cross the line between their 2 plumb bobs. This moment of perfect alignment, a star transit, gave them a true north-south meridian line, a celestial anchor from which all else could be measured. Egyptologist Rolf Krauss explains that these merkits were often used with a bay, a notched stick used as a sighting tool, creating a rudimentary but highly effective observational system. The entire sprawling complex of the Great Pyramid at Giza, its sides aligned to the cardinal directions with an error of less than 1/15 of a degree, was likely laid out using nothing more than these forked sticks and strings. Their method was one of pure patience and geometry. By timing the interval between successive transits of the same star, they could measure the length of the stellar night, and from that derive the solar year with astonishing accuracy. This data was vital, governing the calendar that predicted the Nile's life-giving flood, an event itself heralded by the heliacal rising of Sirius. Inside the tombs, paintings show priests solemnly using the merkit, ensuring the deceased's passage to the afterlife was aligned with the eternal, unchanging stars. The tool was a bridge between the earthly and the divine, a means of maintaining Mot, the cosmic order. Yet, for all its importance, not a single complete merc-hit survives. The wood of the fork and the bay rotted away, the linen strings turning to dust. The metal weight from the plumb line, if it was not simple stone, was likely salvaged. We know of their existence only from tomb art and the enduring, silent testimony of the pyramids themselves, their perfect orientations a ghostly imprint of the instruments that built them. How many other profound insights into early stellar observation were lost when those last wooden merc-hits crumbled into the soil? This elegant proof that minimal tools in skilled hands can achieve cosmic accuracy stands in stark contrast to the next artifact, a device that attempted to bend light itself long before the age of glass lenses. A polished disk of rock crystal lay in the Assyrian dust, its surface still perfectly smooth after 28 centuries. Archaeologists excavating the palace at Nimrud in the 19th century uncovered these mysterious objects, and their true purpose remains one of ancient technology's most tantalizing puzzles. These were the rock crystal lenses of Nimrud, crafted around the 8th century before the Common Era from pure quartz, ground into a convex shape that could magnify a distant object or focus the light of a star. In the royal observatories of Nineveh, a scholar might have held one of these lenses aloft, its clarity allowing him to resolve the faint stars of the Pleiades cluster or to track the slow drift of a planet with a new level of precision. The work of scholars like Giovanni Pettinato suggests these were not decorative items. Analysis shows their curvature is consistent with corrective lenses capable of magnifying small text on clay tablets or enlarging the delicate features of a wax seal. Imagine an Assyrian astronomer, his eyes strained from long nights of observation, using this crystal to check the fine markings on his celestial divination tablet, ensuring the omen for the king was read without error. The crafting process was a marvel of patience. A raw piece of quartz, harder than most metals, was meticulously shaped against an abrasive stone slurry, slowly ground down into a lentil-like form, and then polished for days with ever finer pastes until it achieved optical clarity. These lenses could have been set into simple wooden or metal frames, perhaps held in the hand or mounted on a stand to free both hands for writing. In the flickering lamplight of a scriptorium, they would have been invaluable for reading the tiny, dense cuneiform of astronomical omens, while under the open sky, they might have offered the first glimpse of a star's true nature, not as a point of light but as a tiny disk. The potential for focused observation is staggering. A lens held toward Jupiter could have revealed it as a small, distinct sphere, while trained on the moon, it might have hinted at the rough texture of its Maria, the great dark seas. Modern opticians testing replicas have confirmed these lenses can indeed focus sunlight to a sharp point and magnify text clearly. Their existence suggests a path toward the telescope that was abandoned, a road not taken that lay dormant for over 2,000 years. How might the history of astronomy have unfolded if this Assyrian optical science had continued, if lenses had been paired with the camera obscura or mounted into the first crude telescopes? The destruction of Nineveh and the looting of its palaces scattered these crystal discs, their specific astronomical context lost forever in the rubble of empire. Their obscurity is a profound lesson in how a single, clever invention can vanish, taking with it a potential future where we saw the cosmos clearly centuries earlier. This ancient use of crystal to sharpen human sight finds a strange parallel in the next artifact, where the secrets of the cosmos were divined not from light, but from the cracks in heated bone. The heat of the fire was a question posed to the gods. In the royal courts of the Zhang dynasty, over 3,000 years ago, diviners pressed red-hot bronze rods into the cleaned scapulae of oxen or the polished plastrons of tortoises. The resulting cracks were a celestial language, a divine answer to a ruler's most urgent queries, often about the sky itself. Would the coming eclipse bring misfortune? Was the king's health tied to the moon's phase? The answers were then meticulously carved into the bone or shell, creating the oracle bones that hold humanity's oldest written records of solar and lunar eclipses. Sinologist David N. Keithley's work reveals how these inscriptions, dating to the 2nd millennium BC, are far more than mystical prophecies. They are hard data. A typical inscription might note a divination performed on the day Junction to ask if the following day would be sunny, followed by a verification that on Junction, indeed, 3 flames ate the sun. This phrase, a poetic description of a solar eclipse, was then recorded as a confirmed historical event. The process of pyromancy was a state science. The bones were carefully prepared with hollows drilled into the back to control the cracking, and the heat was applied with ritual precision. The resulting patterns were interpreted by specialized scribes who then carved both the original question and the observed outcome, creating a permanent log of celestial activity and its perceived impact on the earthly realm. The materials themselves were chosen for their durability and symbolic connection to the cosmos, with the tortoise shell representing the dome of heaven and the ox bone the stable earth. For centuries, these bones were stored in royal archives, a growing library of cosmic dialogue. Their accidental rediscovery in the early 20th century, when they were being ground up for traditional medicine known as dragon bones, saved countless fragments from complete oblivion. Scholars can now take a specific oracle bone, like one recording an eclipse in the year 1192 BCE, and using modern astronomical software, verify that a total solar eclipse was indeed visible in the Zhang capital on that exact date. The accuracy is chilling. It proves a continuous, systematic observation of the sky was underway, a calendar system based on lunar cycles and intercalated months to keep the ritual year in sync with the seasons. How do we separate the divination from the science when both were woven from the same thread of human curiosity? The Zhang astronomers were not merely looking for omens, they were building a predictive model of the cosmos, one cracked bone at a time. The tragic fragmentation of these records, with many bones lost to reuse or simply still buried, means we have only a glimpse of this foundational work. As we reach the end of our journey through these 25 lost artifacts, from the geared genius of the Greeks to the cracked bones of China, a profound pattern emerges. Each loss, whether by fire, conquest, or decay, represents a rupture in our collective memory. These objects were not just tools, they were waypoints on humanity's great journey to understand its place in the cosmos. Their disappearance forced us to rediscover, to reinvent, and to sometimes walk paths we had already traveled. What grand unified theory of the heavens might we possess today if this chain of discovery had remained unbroken? The silence left by these lost artifacts is not empty, it is filled with the echoes of what could have been, a haunting reminder that our knowledge is as fragile as the materials we inscribe it upon. A library of cosmic knowledge lies scattered across time, its most brilliant volumes forever missing. Each of these 25 lost artifacts was a chapter in humanity's grand celestial story, and their disappearance left gaping holes in our understanding of the stars. The story of stargazing is not one of steady, linear progress, but a fractured narrative full of dead ends and forgotten beginnings. Historian of science James Burke often illustrates how progress depends on the fragile chain of tools and records passed between generations. When that chain is broken, as it was with the burning of the Great Library of Alexandria or the Spanish conquests in the Americas, we do not just lose objects, we lose the very momentum of discovery. The common threads weaving through these losses are hauntingly familiar. So many of these masterpieces were born from a beautiful fusion of art and science, like the glass celestial globes of Al-Andalus or the illuminated parchment charts of medieval monks, where beauty was inseparable from function. Their survival, or lack thereof, was dictated by the materials that gave them form. The Quipu's knotted cords, the Volvel's parchment discs, the Merk's wooden fork, all succumbed to the inevitable decay of organic matter, while bronze gears and stone stelae fell to the more violent ends of looting and war. The impact of these losses rippled through specific fields for centuries. The suppression of indigenous astronomical knowledge, like that encoded in the Navajo star ceilings, erased entire cultural frameworks for understanding the cosmos. The loss of advanced tools like al-Haytham's specula or Zhang Heng's water-driven Armillary spheres set back the development of observational astronomy and mechanical computation by hundreds of years. Navigation stalled without the refined astrolabes of Al-Battani, and calendar science had to repeatedly reinvent itself after the destruction of foundational records like the Mayan Stelae. Today, we are using modern technology to fill these historical voids. Digital reconstructions and physical replicas, informed by painstaking research, are allowing us to finally read these lost chapters. The Antikythera mechanism's rediscovery alone revolutionized our view of ancient Greek engineering, proving they possessed a technological sophistication we never imagined. This makes you wonder what other paradigm-shattering devices might still lie buried in an unexcavated shipwreck or hidden within a misplaced manuscript. The real lesson is not just about the past, but about our present responsibility. How do we protect today's astronomical heritage, the digital data sets and complex space telescopes, from future oblivion? Every lost tool carried with it more than just data. It held the spirit of inquiry, the spark of curiosity that drove its creation. As we look up at the night sky with our modern apps and powerful telescopes, we are participating in that same eternal conversation, one that depends on preserving the fragile instruments of our wonder for the generations of stargazers yet to come. Our journey through these 25 lost artifacts reveals a profound truth about our relationship with the cosmos. From the intricate gears of the Antikythera mechanism to the prophetic cracks in Zhang oracle bones, each object fundamentally reshaped how humanity saw its place in the stars. This was never just a scientific pursuit. It is a rich cultural tapestry woven with threads of brilliant innovation, heartbreaking loss, and persistent rediscovery. The fragility of knowledge itself is the key takeaway, a reminder that every tool and record is a vulnerable beacon in the long night of history. We are the custodians of this cosmic heritage, responsible for ensuring the chain of discovery remains unbroken for those who will look up after us. The astrophysicist Neil deGrasse Tyson offers a beautiful reflection on this legacy when he says, "The cosmos is within us. We are made of star stuff." This is not merely poetry. It is a physical truth that connects our own existence to those ancient observers who first sought to decode the heavens. Their curiosity is our inheritance. You can honor this legacy by visiting a local planetarium, by supporting archaeological and preservation efforts, or simply by stepping outside on a clear night to gaze at the stars with a renewed sense of wonder. Think of the countless hands that built the tools to understand that very sight. If this exploration into our forgotten celestial past resonated with you, subscribe for more deep dives into the mysteries of space. And we would love to hear from you. Which of these lost artifacts captured your imagination the most? Share your thoughts in the comments below, and let's continue this conversation across the cosmos.